All right, everybody. This is 6.2, one-to-one functions. This section is really important because we learn about one-to-one functions and inverses. And in order to have an inverse, you need to be a one-to-one function. So what does it mean to be one-to-one? So, a bunch of definition on this page, right? A function is one-to-one if any two different inputs in the domain correspond to two different outputs in the range. That is, if x1 and x2 are two different inputs of a function, then f is one-to-one if and only if the y value of x1 does not equal the y value of x2. Keeping it simple, what that means is that every x in the domain has one and only one y value in the range. So for one x, there is only one y. This is what it's meant to be a one-to-one function, okay? And down below, we'll look at the globs and see what a one-to-one function is, what a function is, and what not a function is. So A, the two globs here, represent a one-to-one function. X goes to y1, x2 goes to y2, x3 goes to y3. Every single x has its own y value, its own separate y value. So this is what we're focusing on today. One-to-one functions. Okay. The second glob, it's a function, but it's not a one-to-one function. So x going to y1 and x2 going to y1, that is a function. So to be a function, multiple x values can share the same y value. So this is a picture of a function, but it's not a one-to-one function. And the third glob is just not a function at all, because now we see that one x value has two y values. Now that's just greedy. And since that's greedy, we can't have a function. So to not be a function means that one x value has multiple y values. So that is the definition of not a function. Okay, but just remember, today is all about one-to-one functions. Every single x has to have its own y value. So let's look at the coordinates below and determine whether we have a function, a one-to-one function or not. So for the first set of coordinates here, -2, 6, -1, 3, 0, 2, 1, 5, 2, 8. All of these x values look like they have their own y value, So is this a one-to-one function? Yes. The next set of numbers, 2, 6, -3, 6, 4, 9, and 1, 10. Does every single x value have its own y value? And that answer is no. And we see it right here. 2 goes to 6, and -3 goes to 6. So we see that two x values have the same y value. And this is not the representation of a one-to-one function. So we will say no. Because if you're one-to-one, every x value has its own y value. Okay. Another way to tell if you have a one-to-one function is by the horizontal line test. This means you'll graph the function, or you'll be given the graph of a function, and all you have to do is draw a horizontal line through it. And if this horizontal line intersects only once, you have a one-to-one function. If this horizontal line intersects more than once, you do not have a one-to-one function. So let's see what that looks like. Okay, so let's look at the graph of x squared. X squared, we know, looks like this. And if I draw a horizontal line through it anywhere, no matter where, we always will intersect twice, more than once. Therefore, x squared is not a one-to-one function. Because this means two x values share the same y value. Okay. Then let's look at the graph of x cubed. X cubed, we know, is that squiggly line, right? That S curve. So it would look something like that. And if I draw a horizontal line through it anywhere, we see that we only intersect once. We only intersect the line once, meaning that x cubed is a one-to-one function. Okay. And little theorem down here. A function that is increasing on an interval I is a one-to-one function on that interval. So we see that if you look at the graph of x cubed from left to right, x cubed is an all-increasing function. Therefore, it's one-to-one. The same can be said for an all-decreasing function. If that was negative x cubed, then it would look like this. And no matter if you drew a horizontal line through it, you would only intersect it once. So an all-decreasing function is also a one-to-one function, which we can use that theorem to refer to x squared. X squared is a decreasing and increasing function. Therefore, is not considered one-to-one. It either has to be all increasing or all decreasing. So there you go. That is the definition of a one-to-one function. Okay. So now we're going to get into the important definition of what it means to be an inverse. It's really cool. Okay. So suppose that f is a one-to-one function. Then to each x in the domain of f, there is exactly one y in the range. So let's see what that's talking about, right? So look at my blobs down here. And we only focus on these parts for right now. So here's my domain. So here's my x value. And what we're saying is that this one x value, if it's a one-to-one function, correlates to, so this one x value in the domain of f correlates to one y value in the range of f. Well, what this must also mean is that, well, hey, there also has to be one y in the range of f that correlates to one x in the domain of f. So we're just saying it backwards, right? So if you're a one-to-one function, then there's an x that relates to one y in the range, and there is a y that relates to one x in the domain, which is exactly what the paragraph says, right? The correspondence from the range of f back to the domain of f is called the inverse function of f. So what we're saying with all that is that in order to get from x to y, in order to get from the domain of f to the range of f, if it's one-to-one, we use f, right? Function f, we input an x, it'll output a y for function f. And then what we're saying that, well, if this is an inverse and it's 1-to-1, then what we're saying is that, well, in order to get back from the range of f to the domain of x, in order to get back there, we use the inverse function. And this is denoted by the symbol, which looks like f raised to the -1. That's not how we say it. If you see this symbol denotes the inverse. So the way you say this is you say f inverse, or inverse of f. And with that being said, so if we got from x to y using f, then to get from y back to x, we use f inverse, or the inverse of f. Now, two facts are apparent, that once you apply the inverse, look at our blobs, y now becomes the domain of the inverse. So the range of the original function now becomes the domain of the inverse function. And once we go from the domain of the inverse to the range of the inverse, another fact is apparent. The domain of the original function becomes the range of the inverse. So to keep this really simple is that if you have a 1-to-1 function, and if you apply the inverse function, then your domain and range of the original function will swap, and they will become the domain and range, or better yet, the range of the original function will become the domain of the inverse, and the domain of the original function will become the range of the inverse. That's it. That's everything this says right here. The domain of f becomes the range of the inverse. The range of f becomes the domain of inverse. So domain and range just switch places. That's it. Okay. Now, to verify that two functions are inverses of each other, we see from the above diagram, my blobs, that if we start with x and use the original function f, we get to the range. And then, if you apply the inverse, we come back to x. So what it's saying is that we start with x, we apply the original function f, and we get to y. And then if we apply the inverse function, we will always arrive back at x. So, in order to prove, now we're going to use this to prove that functions are inverses of each other. So in order to prove that functions are inverses of each other, we are going to compose them with each other. And if the result ends in x, we know that these are true inverses of each other. So down below, we see that if you take the inverse and compose it with the original function f of x, if they are true inverses of each other, then the end composition results as an x. And of course, since we're dealing with a composition, the inverse would have to take the domain of the original function, because that's how compositions work, right? So whenever f inverse composes with f, f inverse has to abide by the domain of f. Okay. And then the same could be said the other way. If you do function f and compose it with the inverse, then if they are true inverses of each other, you should arrive back at x, where x is in the domain of the inverse. So now if f composes with the inverse, f has to take the inverse's domain. Okay, so let's go ahead and try these examples out. First up is we want to verify that these two functions are inverses of each other. So g of x is x cubed. Inverse of g is the cube root of x, right? or G inverse of X, however you want to say it. Inverse G of X or G inverse of X. Doesn't matter how you say it, as long as you know that it's the inverse. Okay, so we want to prove that these are inverses of each other. So we'll go this way first. A, we'll say G compose G inverse of X. And then we'll write it as G of G inverse of X. Now remember how compositions work. The inverse G function is the cube root of X. So that's what's going in my parentheses next. G of the cube root of X. And now we take the cube root of X and plug it in for X into function G. So we will get parentheses, the cube root of X cubed, which will leave us with X. Hey, look at that. We arrived at X. So this means that when we compose one way, we know that these have to be inverses of each other. But just to double check it, let's compose it the other way. We'll say G inverse composed with G of X. This will give us G inverse of G of X, which will give me G inverse of, and remember that G of X is X cubed. So you'll get G inverse of X cubed, and now X cubed goes in for that X. And we'll get the cube root of X cubed, which will leave us with X. And there you go. That's how you prove if two functions are inverses of each other. Now, do you have to prove it going both ways? Probably not. You can probably only prove it by showing one step, but it's good. Double verification lets you know that these are inverses of each other. Okay, which means we'll try that on the next one. Verify that these functions are inverses of each other. So, oh my goodness. Oh, we're going to plug a fraction into a fraction, y'all. Okay, so verify that the inverse of f of x equals 2x plus 3 over x plus 4 is g of x equal to 4x minus 3 over 2 minus x. So they didn't write it as the inverse with the inverse notation, but the point is, let's go ahead and compose these two to see if they are inverses of each other. So A, we're going to say f compose g of x. And then we get f of g of x. And then you'll get f of, and g of x is 4x minus 3 over 2 minus x. Okay, and I'm choosing a different color because this is gonna get messy. You're gonna take a fraction and plug it into the other fraction for every x. So yes, all of this gets plugged in for that x and that x. Okay, so be careful when plugging this in. So now we're gonna have 2 times 4x minus 3 over 2 minus x plus 3 over 4x minus 3 over 2 minus x plus 4. Okay. We have plugged it in for every x into function f. This is very conceptual, very hard to look at. So just make sure you take your time with this. Okay. So they plugged in, we have them in, and now it's cleanup time. So what I'm going to do first is put 3 over 1 and 4 over 1 and multiply by the common denominator of 2 minus x over 2 minus x. And same thing down here. Okay, next step, I'm going to distribute that 2 in the numerator, because I can even put this 2 over 1. And if I distribute that 2, you'll get 8x minus 6 over 2 minus x plus, and also, I'm going to distribute that 3. Why not? 6 minus 3x over 2 minus x. And now we worry about the denominator. 4x minus 3 over 2 minus x plus, and in this same move, let's go ahead and distribute that 4. 8 minus 4x over 2 minus x. Gotta love all that fraction work, right? Oh, look at that. Hopefully I got more room. Okay. Now, clean up. We have the same denominator. So the same denominator in my numerator, which means you can combine the numerator of the numerator. Yeah, right? So you'd get 8x minus 6 plus 6 minus 3x over 2 minus x over, same thing down below, 4x minus 3 plus 8 minus 4x over 2 minus x. Hey, still got some room. Now, clean up some more. Clean up that numerator, clean up that numerator, and I should be left with, let's see, your 6's will cancel, and 8x minus 3x will give me 5x over 2 minus x over, same thing down below, 4x's cancel, negative 3 plus 8 gives me 5 over 2 minus x. We're almost there. Fraction over a fraction, you have fraction cake, and the only way to get rid of fraction cake is to multiply by the reciprocal. And let's see, can I write any smaller? I don't think so. So what we're gonna get is, actually, I got a little bit of room up here, right? You're gonna get 5x over 2 minus x times the reciprocal of the denominator, 2 minus x over 5. And now watch the magic that happens. 2 minus x's are gone. 5's are gone. What are we left with? that lonely single x. So this verifies that f of x and g of x are inverses of each other. Now I said we can get away with this by just showing one route, but I'll leave it up to the viewer. I'll leave it up to you, the student, because it's great algebra practice. Try going the other way. Do G compose with F and see if you arrive at X. Me, I believe they're inverses of each other, but you shouldn't. You should check. So I leave it up to the viewer to compose G with F. And if you have questions over it, definitely ask in class. Okay, moving on. All right. Next theorem. If you have a one-to-one function and you graph it, well, what we know now is that one-to-one functions have an inverse. And if you graph them both on the same plane or the same graph, then you will notice that the inverse function and the original function are symmetric to the line y equals x, as shown in this lovely picture below. So your one-to-one function and the inverse of that one-to-one function, if you graph them together, they are symmetric about this line, y equals x. And you could show it. Let's say that, what do we have? It's not accurate, but I'll make it into a point. Let's see, let's look at b. So this b is 1, 2, 3, 4, 5. This b is 5, 0. So if you reflect it over the y equals x line, you'll get this b, which is 0, 5. That's how this works. Okay, let's just say, what is that, -1, almost -2. So this point, let's just say is 0, -1.8. And if you reflect it over the x-axis, then you'll get this point, -1.8 and 0. So inverses and their original function are symmetric over the line y equals x. You just reflect points across them. And remember, inverses and one-to-one functions, their domain and ranges flip, they swap, they switch, which means remember that domain is x and range is y. So if you look at this point 0, 5, which is xy, if you have your inverse graph, your x and y values switch places. Your domain and range values switch places. And that's why this becomes 5, 0. X and y switch places. With another fancy word, they interchange. Okay. So now let's go ahead and graph the original function and then find its inverse function. So graph the points -2, -1, -1, 0, and 2, 1. Graph the line y equals x, and then graph the inverse. Okay, perfect. So -2, -1, let's see. -2, -1. Right there. -1, 0, right there. And 2, 1, right there. Okay, so here's what my original function looks like. I wonder if I should space it out more. I probably could. Let's do that. Let's make this 0, 1, 2, -1, -2, and then down here is -1, -2, and then 1, 2. There you go. I'll make use of my room. Okay, plot them again. -2, -1, -1, 0, and then 2, 1. Hey, that looks better. Probably should be a little more. There we go, something like that. Okay, and then it says to graph the line y equals x. So remember that y equals x is the line that's 1 for 1. If x is 1, y is 1. If x is 2, y is 2. If x is 0, y is 0. If x is negative 1, y is negative 1. So let me just draw that line here. 1, 1, 2, 2, 3, 3, negative 1, 1, negative 2, 2. There you go. Here's our line. Y equals x. And all we want to do here is graph the inverse of this one-to-one function. And first off, is this a one-to-one function? And since we have the graph, or we even have the points, does every x value have its own y value? That answer is yes. Therefore, it's one-to-one. If you still don't believe it, you can do the horizontal line test. Draw your horizontal line anywhere through this function, and we will only intersect it once. Therefore, our line, our graph, is a one-to-one function, which means we can find its inverse. So if we're given the point, here we'll do this, right? So if we're given the point -2, -1, well, if it has an inverse, remember that its x and y values will swap. So you'll get -1, -2. You'll get 0, -1, and you'll get 1, 2. So now we'll know which points apply. So -1, -2, down here. 0, -1, right there. And then 1 and 2. And let's see what that looks like. And now, I must ask you, or myself, since I'm talking to myself, do these look symmetric about this line y equals x? And that answer is yes. Good. These points reflect over each other, these points reflect over each other, and these points reflect over each other. So this graph looks pretty symmetric because these functions are definitely inverses of each other. Okay, good fun. There you go. Okay, f inverse of x. Okay, so that's graphically. And now here's my favorite part, because we can do graphs all day. Graphs are easy. The best way to check for an inverse is to do it algebraically. Now, that's what we want. We want to build our algebra skills. So let's find an inverse function defined by an equation. The fact that graphs of a one-to-one function and its inverse are symmetric with respect to line y equals x, we can obtain the inverse by interchanging, there's that fancy word, the roles of x and y in f. And there's a couple steps to do this. Step 1, replace f of x with y. Step 2, interchange the roles of x and y. Step 3, solve for y. And step 4, check your work. Okay, so of course, I'll walk you through all these steps and how we find the inverse. Okay. So first thing to do This says find the inverse of the function x cubed minus 1, and then graph him. So what we want to do first is let's go ahead and graph the original function first. So let's graph x cubed minus 1. So that's what we'll start with. I'll say A. And we're going to graph it. So I'll just make a small XY chart. And to graph this, I'm just going to choose the most common numbers when graphing. -2, -1, 0, 1, 2. Now plug these into the function. -9, -2, -1, 0, and 7. Now let's go ahead and plot that on the graph. And for these, I'm not going to change any intervals. I'm going to leave these the same. So -2, -9, that's down there. -1, -2, 0, -1, 1, 0, and 2, 7. 1, 2, 3, 4, 5, 6, 7. So here's what the original function looks like. This is f of x. Okay, and while we're at it, let's go ahead and find the domain and range of this function. Well, this function looks like it's fully continuous and for all x values, and also both tails, one tail heads to negative infinity, the other tail heads towards infinity. So what we're going to say is the domain is all real numbers, and the range is all real numbers. Okay, perfect. That was easy. Now let's find the inverse. Okay, I can do that below. Okay, x cubed minus 1. All right. So B, find the inverse. All right, first step to finding an inverse. Step 1, change it into y equals x cubed minus 1. That's step 1. Step 2 is probably the most important part. Step 2, since this is a one-to-one function, oh yeah, I wouldn't even check to see if it was one-to-one. Like why are we going to find an inverse if we don't know it's one-to-one? Well, look at this. First off, it's all increasing, which by the theorem, this should be one-to-one. By the horizontal line test, we only intersect once, which means it's one-to-one. By our XY chart and our graph, we see that so far, every x has its own y value. So this means it is one-to-one, and we are cleared to find the inverse. Okay, back at it. So step 2, like I said, is important because if it's one-to-one, then it definitely has an inverse. And if it's an inverse, we are going to interchange the roles of x and y. So step 2 is where we interchange. And all we do is we write it as x equals y cubed minus 1. We have interchanged the roles. And now, step 3 is solve for y, which means that if we're going to solve this for y, I'll put that in here, solve for y. So x equals y cubed minus 1. You're going to add the 1 over, x plus 1 equal to y cubed, and then you are going to cube root both sides. And we will end up with the cube root of x plus 1 equal to y. And the way we will finish step 3 is you will write it as the inverse. So we are going to say f inverse of x is equal to the cube root of x plus 1. There it is. There's the inverse. Okay. And now all we have to do is graph it. Well, what's beautiful about one-to-one functions and their inverses, if you already have the coordinates for the one-to-one function, then you already have the coordinates for the inverse, because all you have to do is take that XY chart and flip it around. You swap it, right? So for the inverse, I got room up here, right? So for the inverse, the XY chart, I'm writing too big. Fix it. One moment. You'll have -9, -2, -2, -1, -1, 0, 0, 1, and 2, 7. Or 7, 2. There you go. You just take them and you swap them, flip them, switch them, whatever you want to say, right? Okay. And now all we have to do is plot it. So -9, -2 there, -2, -1 there, -1, 0, 0, 1, and 7, 1, 2, 3, 4, 5, 6, 7, 2. And there is f inverse of x. Okay. And then one more thing to note is the domain and the range. Well, we see that this is a fully continuous function, and both tails, this tail is headed towards negative infinity, that tail is headed towards positive infinity. So if you looked at the domain and range for the original function and you swapped them, well, we're gonna get the same exact thing for the inverse. So here, domains negative infinity to positive infinity, range is negative infinity to positive infinity. Okay. And step 4 does say check your work. Hey, at this point, I'm a believer that we got it right, because one way to check it is, does our graph look pretty symmetric about the line y equals x? Look at that. That looks symmetric, right? This point is 7, 2. That point is 7. So we're pretty symmetric. Okay, excellent. So that is how you find an inverse algebraically. And we're going to do it again on the next page. So find the inverse function. We are given f of x equals 2x plus 1 over x minus 1. Find the domain and range, and find the inverse and check the result. Okay. So first off, we can get rid of what the domain and range is for function f. So for f of x, here our domain, we can see is x not equal to 1. And our range, how can we figure out our range without graphing it? Well, let's think about horizontal asymptotes, right? Let's think about horizontal asymptotes. So the degrees on these x's are equal. Therefore, that's rule 2 of horizontal asymptotes, which means that our horizontal asymptote would be the line y equals 2, which means that if we were to graph it, you would start at negative infinity, come up, stop at 2, and then continue on towards infinity. So for my range, we can just say y not equal to 2. Okay. And I'll show you another way to get it in case you don't know how to find the range, right? And that'll all come when we find the inverse. So let's go ahead and find the inverse of this function. Okay, and we'll go through the steps. Step 1, change it into y equals 2x plus 1 over x minus 1. Step 2, interchange. We're going to make it x equals 2y plus 1 over y minus 1. This is the interchange part. Step 3, solve for y. Did I say solve for y on the last one or x? I said y. Good. It's been too long. So x equals 2y plus 1 over y minus 1. So in order to solve for y, we need to get y out of the denominator. So what I'm going to do is put x over 1, and let's go back to elementary school and cross multiply. Which will give me x times y minus 1 equal to 2y plus 1. Okay, and now we must remember what we're solving for. So on this point, we are still solving for y. So you, as a student, are going to do your favorite thing that you're probably not thinking about because you're thinking way too hard on how to solve for y. The next step here is you're going to do what you love to do. You are going to distribute. Yes, I said it. You are going to distribute this x to both terms. It has to be done. There is no other way to solve for y. You must distribute this x. So we're going to get xy minus x equal to 2y plus 1. Now, once again, what variable are we solving for? We are solving for y. So now we are going to put all our y terms together, which means I'm moving this 2y over, and I'm moving that x over to the right. So I should get xy minus 2y equal to x plus 1. And again, I'm going to remind you, what variable are you solving for? And you are going to say y. You are solving for y. So what can you do on the left side? You can factor out a y. We take a y out, and you're left with x minus 2 equal to x plus 1, and all you have to do now is divide by x minus 2. And y equals x plus 1 over x minus 2. And now we are done. We have found the inverse, and we write this as f inverse of x equal to x plus 1 over x minus 2. And now, looking at this, the domain we see is x cannot equal 2. The range, and without thinking, okay, so now let's look at the range of this function without thinking of horizontal asymptotes. Let's look at the original function's domain and range. The domain of the original function is x equals 1, not equal to 1. And remember, if you have the inverse of each other, then the domain of the original function becomes the range of the inverse function. What? I know, exciting. So this means that our range is going to be y can't equal 1. And now, if you check it by horizontal asymptotes, that makes sense because the degrees are equal. Therefore, your horizontal asymptote would be y equals 1. Hey, look, it all checks out. And let's say we didn't know how to find the range in the beginning. Then that means when you find the inverse, the domain of the inverse becomes the range of the original function. They switch places. Oh, done. Okay, there you go. Nothing else to it. It does say check your result, but I'm pretty sure I'm good. You, as a student, check it out. I'm just moving on. We found domain and range. We found the inverse. I believe my algebra is good enough. Let's move on. You, though, you should check it. And if you don't know how, then ask questions, please. All right, we made it to the last one. Finding the inverse of a domain restricted function. Now, this one is pretty cool because we use it in pre-cal. So we saw from earlier on the very first page that x squared was not a one-to-one function because if we draw a horizontal line through it, we intersect it twice. But here's where math gets really cool. It is possible, it is very possible for us to restrict the domain of any function, so if we are able to restrict the domain of a function, this means that we are able to make any function into a one-to-one function by restricting its domain. Crazy, right? We have that power. We are the almighty math power mathematicians, okay? Not ticians, mathematicians. So if we restrict a function's domain, then we make it a one-to-one function. And this becomes very useful in pre-cal because trigonometric functions go on infinitely. And we have to find a restriction to make them one-to-one so we can find their inverses. So this isn't trig today. This is just algebra. And I'm showing you the power that you have. You can restrict a function's domain. You can restrict any function's domain to make it one-to-one. And if you make it one-to-one, this means it will definitely have an inverse. Okay, so we are given the function here, x squared plus 1. But we are restricting its domain to x greater than or equal to 0. So we're given f of x equal to x squared plus 1, and we say, hey, let's restrict it to x greater than or equal to 0. And restricting it to have nothing but values greater than or equal to 0 will make this function a one-to-one function. So let's check that out before we even try to find the inverse. Okay, so here's my x squared. I'll draw my little graph. There we go. All right, and x squared plus 1, so let's see. Where my domain is x greater than or equal to 0. So if I made a small xy chart for this, we are only allowed to choose numbers from 0 to infinity. So 0, 1, 2, 3. That's probably all I need. And if I plug in 0, I get 1. If I plug in 1, I get 2. If I plug in 2, I get 5. And if I plug in 3, I get 10. Okay, so I'll have 0, 1, 2, 3, and then probably should graph this somewhere else, but we'll graph them together after. Okay, and then I go up to 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I think I actually have to graph below, but I just want to show, no, never mind. Is there a graph below? There is, my bad. So this will help me graph in the same axis. Sorry, my bad. So we have the points plotted already. I'm not going to skip intervals, so let's plot this function. 0, 1, 1, 2, 2, 5, and 3, 10. And here is my x squared function. That we have restricted to only have values greater than or equal to 0, which means that my x squared function, due to a domain restriction, is now a one-to-one function. It's phenomenal, right? So we only intersect once with our horizontal line test. Which means that if this function is one-to-one, then it definitely has a what? It has an inverse. Okay. And also based on this graph, we see that my range is y greater than or equal to 1. Because we start at 1 and we go to infinity. Okay. Let's find the inverse. We'll go through all the steps again. I can probably fit that right here. One, y equals x squared plus 1. 2, interchange x equals y squared plus 1. 3. Solve. I'm going to move that 1 over, and you'll get x minus 1 equals y squared. And then we'll square root both sides. And we are going to end up with plus or minus square root x minus 1 equals y. But which one do we pick? Do we pick the positive or the negative? Well, look at my original domain and range. Everything here tells us that no matter what, our values are always going to be positive. X greater than 0, y greater than 1 means nothing but positive values. So for this one, we only choose the positive. And therefore, my final step is f inverse of x is equal to the positive square root of x minus 1. There it is. And we can get the domain and range already without graphing it. You take these domain and range from the original function and you flip them, you swap them, you switch them, you trade them out, you interchange them, whatever other words you want to use, which means now my domain will be x greater than or equal to 1, and my range will be y greater than or equal to 0. Now let's graph. By using that same XY chart, all we're going to do is switch out the values. 1, 0, 2, 1, 5, 2, 10, 3. Okay. And also, another way to check to see if you're doing it right, take these x values and plug them into your inverse. And if you get the output of these y values, then we're doing it right. If I plug in 10, you'd get the square root of 10 minus 1, which would give me the square root of 9, which gives me 3, which is right there, 10, 3. So this means we are definitely doing it right. Okay. Now let's plot 1, 0, right there, 2, 1, right there, 5, 2, 1, 2, 3, 4, 5, and 10, 3. And there's f inverse of x, and then I'm going to draw my line y equals x. And do we look pretty symmetric? Look at this. That point is 1, 0. This point is 0, 1. We are definitely symmetric. And these are definitely inverses of each other. Okay. I can get rid of that stupid graph, sorry. Whatever I was thinking with that, okay? And then that's it, guys. Those are one-to-one functions and their inverses. Nothing else to it. There is a little composition in here. Again, the only composition you should be doing is to check and see if they are inverses of each other, which I did in the beginning. But again, for you guys, you should definitely check because it is definitely a good algebra builder. It'll make you more confident in your algebra skills. Look at that fraction one. Brutal, right? But simple if you take it step by step. Okay, that's it. See you at the next one.